We will start today with section 18.2, which is galvanic cells or voltaic cells. So there are two names for the electrochemical cell that we're going to talk about. You can call them either galvanic cells or voltaic cells. It's the same idea. What it is, it's a device that uses chemical energy to create electrical energy, and it's from a spontaneous reaction. So what you have over on the left-hand side is an example of an electrochemical, cell. Okay, so this right here, and we're going to work on drawing these and learning sort of all the components of one of those and seeing how it works. But that's an overall electrochemical cell. Now, when we consider this as being a device that uses chemical energy to create electrical energy, we've got something to think about before we actually look at how the device is set up compared to, say, or basically how the device is set up in a useful way. So what we have in the device, what you can see here is you've got some zinc metal, okay? You've got a solution that has zinc in it. You've got some copper metal and a solution that has copper in it. And so one of the things you could think about is if you had instead a beaker, for example, that had, that's a terrible beaker. We can do that again. Okay, so you have a beaker here, and inside the beaker you've got some water, and inside the water you might have some, let's say, zinc ions and some copper ions. Well, in that instance, both zinc and copper like to be in the +2 oxidation state, so really nothing is going to happen. If you were to then take and put in a piece of zinc metal, just drop in a piece of zinc metal, okay. So zinc solid, and drop in a piece of copper metal, you could get a reaction to occur. And the reaction that would occur would actually be this. So if you look at what happens in this instance, within this solution, you have these zinc ions and these copper ions. And what would wind up happening to those concentrations is those concentrations would change because there would be a chemical reaction that takes place. And the chemical reaction that would take place spontaneously would be some version of the zinc solid becoming zinc 2+, or the zinc 2+ becoming zinc solid, with the combination of either the copper 2+ becoming copper solid or the copper becoming copper 2+. Only in this case, a reaction would occur in one direction or another. So you could have the following two reactions here. You could have zinc solid plus copper aqueous, copper 2+ aqueous, reacting to form copper solid plus zinc 2+ aqueous. Or you could have copper solid plus zinc 2+ aqueous reacting to form zinc solid plus copper 2+. So you could have this reaction go in either direction, or you could have either of those two potential reactions is what I should say. But only one of those reactions is going to occur spontaneously. And it turns out the one that occurs spontaneously is the one whereby the zinc solid becomes oxidized, right? And the copper solid forms, or rather the copper 2+ becomes copper solid. And so the way that would work is the copper would plate out on the zinc metal. Basically, you'd start to get copper that would accumulate on the zinc metal in this solution as the zinc metal itself began to dissolve. And so as this chemical reaction occurs, you would cover this whole piece of zinc metal with some copper, okay? Now there's a reason why that chemical reaction would go in that direction. There's this thing that we're gonna explore called the reduction potential. It has to do with the chemical potential of the reactants and products in these reactions. Basically, copper wants to be a solid more than zinc wants to be a solid. And so the reaction is going to be driven by this thing that we call the potential, the cell potential. Only in the example down here, right, where they're all in the same solution, that all of the reaction occurs at the interface of the solid zinc and the solution, right? Because the redox reaction whereby electrons are transferred occurs just locally at that interface. But we can actually do this in such a way that we can make this much more useful. And the way we do that is we separate this chemical reaction into two half reactions. And essentially what you do in this is you can see from each of these parts is you take the zinc components of it and you put those in one beaker, and you take the copper components of it and you put that in a separate beaker, and then you connect them using two things. One of those two things that you use to connect them is a wire. So you can see there's a wire here, right, up top. And we'll draw this out a little bit later, but there's a wire, and that wire is going to conduct electrons. So the electrons can move from one place to another. And the other thing that connects them is what's called a salt bridge, which is this right here, which if electrons are moving, in order for the chemical reaction to occur, right, in this case it's a redox reaction, so the electrons moving is what you want. But if your electrons were the only thing that was moving, you would start to build up charge. And when you build up charge, especially if you're considering all of those, right, in the wire up here, right, all of these electrons to be moving only in one direction, if that were to occur, you'd build up a bunch of negative charge over on the right side very, very quickly, and that would stop the reaction from occurring. And so there's this other piece that we're going to call the salt bridge that'll connect the two reactions and allow the charges to stay neutral overall, which will allow a chemical reaction to occur. And so by separating this overall chemical reaction into two half reactions that are connected, you can control how that oxidation occurs and actually do something really useful with those electrons. That's the key here, is do something useful with those electrons that are moving from one place to another. And the useful thing that you're going to do with those electrons, well, those are little pieces of matter that are moving, and little pieces of matter can do work, right? So a force times a distance, right, is the work that those electrons are doing. And the work that the electrons are doing is because there's this potential energy difference between the two sides of this cell, okay? So that's the overall underlying theme for utilizing chemical reactions to do work, and thus causing a spontaneous reaction that we can sort of harness that energy by doing other things with the electrons. In particular, we can put those electrons into a battery to charge a battery. We could put those electrons into a generator to generate electricity, or we could utilize those electrons to do other things like a motor, right? So if those go into a motor, you start spinning the motor, you can start using that motor to do other amounts of work, okay? But the overall scheme here is there's a chemical reaction that drives there's a chemical reaction that is utilized to do work, basically, okay? Now, the cell potential, it's also called the electromotive force, or EMF, and it's abbreviated with an epsilon or a capital E, could be either one depending upon the source that you're looking at. That's the driving force of the cell. That's what causes an electrochemical cell to go in a spontaneous direction, okay? And in that spontaneous direction, you'll have an oxidizing agent, right, which is being reduced. And that oxidizing agent is pulling electrons away from the reducing agent because it wants those electrons more. And so we're going to have some values that we can use to compare which element is a better oxidizing agent or which element is a better reducing agent. And those are things we'll look at once we get a little bit more of these tools under our belt, okay? Some other things that we should know. So we would measure the potential difference between these cells, the electrochemical potential, okay? Again, we're talking potential energy here. And we would measure that using what's called a potentiometer. And the volt is the measurement for the potentiometer, okay? And 1 volt, and we're going to come back to this a little bit later, 1 volt is 1 joule, okay, per 1 coulomb. So it's essentially an amount of energy over the charge, okay? So essentially it's an amount of energy that you can get per amount of charge that moves from one place to another, where the coulomb, okay, the C, right, we, back in 101 when we did, well, I guess we may not have actually looked at the coulomb, but the coulomb is the measure of the SI unit for charge, okay? So, now, let's talk about those half cells, or the 2 reactions that are taking place here. You can see the direction of a reaction based on this particular drawing, such that the electrons are moving from the left side to the right side. And so you know what's going on there is that the zinc is losing some electrons. So zinc solid, this is on the left side, zinc solid is changing from zinc solid to zinc 2 plus, that's aqueous because it'll dissolve, and it's giving up 2 electrons. On the right side, you've got, well, if the electrons are moving in that direction, what's happening is the copper 2 plus, aqueous, is using those electrons as they come from one spot to another, or it's pulling those electrons over, is another way to look at it. So it's pulling these electrons to form copper metal. Okay. Now, this is a spontaneous reaction that has to do with something we're going to call the reduction potential of these substances. But there are a couple things to label here. On the left side, this is zinc being oxidized, right? So oxidation occurs. Okay, so on the left side, this half cell on the left side is called the anode half cell. Or the anode compartment. Okay, this little piece of metal here with the zinc is called the anode. Okay, and the anode is an example of an electrode. Okay, an electrode is really just a piece of metal or conductive other substance okay, where a chemical reaction is going to take place. And so the anode is where the oxidation occurs, or the oxidation takes place. Okay. The other side is what's called the cathode, right? Which is where the copper side is, right? And the cathode is where reduction occurs. Okay. And so at the cathode, reduction takes place. Okay. And so the side that has the copper in it is the cathode half cell. Or the cathode compartment. Okay. And the electrode here, this piece of copper metal, is the cathode. Okay. And so that's where the chemical reaction where the copper starts to form and make the copper metal in this case as the electrons. So as the electrons flow from the cathode to the anode, the piece of the copper metal will get heavier, right? The copper solid will become more massive as the reduction occurs. Essentially, we call that, we have a way of discussing that. We say the copper plates out. Okay. And so the plates out comes from, like, if you've ever heard of electroplating, like if you have, let's say, you know, families would have silverware, right? There was actually real silver. And if they had pure silverware, right, that silver was probably very expensive, but a cheaper way of doing it is just getting a piece of metal and coating it with a very thin layer of silver. Means that you're not using as much of a precious metal. And so we say it plates out, right? And so your copper, you'd be plating out copper, or doing copper plating. While that copper cathode, right, that is the copper cathode that gets more massive, the zinc solid anode is going to dissolve. Okay. And so these are some things that occur during this electrochemical process, okay, or this chemical reaction that occurs. Now, as that happens, remember these electrons are moving from one side to the other side, right? They're moving from the left side to the right side. So as those electrons are moving, you would start to build up charge over on this electrode if they weren't connected by this thing in the middle that we call our salt bridge. And for the salt bridge to really work, what has to happen, well, and what the salt bridge is, we'll first sort of talk about that. The salt bridge is some sort of a gel or porous substance that allows ions to move from one side to another, or in one direction or another. And its purpose is to balance charge in these half reactions. Now, that salt bridge could be like a gel that allows for the flow of these ions. It could be a piece of paper that, like a filter paper, that allows for a solution of ions to stay wet and move, but it's basically a porous substance that allows the ions to move. And so that's going to cause the charge to balance. So as electrons are moving through the wire from left to right, a negative charge has to be moving over from right to left to balance that. So the sulfate ions in this particular diagram would move from right to left. And you can also have the sodium ions, which is a positive charge, moving from left to right, along with those electrons, in order to keep the charges in these two half cells balanced. So you would also have, notice each of these particular half cells has a counter ion to it. All that counter ion is when you dissolve the zinc 2+ and copper 2+, right? It's the ion that dissolved with it, right? It's part of that salt, okay? Now the salt bridge doesn't have to be anything involved in the reaction. In fact, you want that salt to be inert. You don't really want it to react at all because you just want the salt bridge there to allow the charge to balance, okay? But that's the basic setup of an electrochemical cell, right? So you have two half cells that form an electrochemical cell. Okay, now this is something you should generally be able to draw as well. Okay, and so I just want to sort of draw this as well as I can for you and label the components of it a little bit more, right? So this is, and I do this in here, we had the pictures over there, but I want to prove to you that it's really not too hard to draw one of these. Okay, so you'll have two compartments. So these are your beakers essentially. So in each of these beakers, you're going to have a solution. You'll have some sort of a liquid in there. Okay. The solutions will be connected by a salt bridge and by the wire with the electrodes. So the salt bridge often is a U-shaped tube, okay, that has a gel in it, or it's, you know, a piece of paper that just is kind of hung over the sides of the two beakers to connect the two solutions. Okay, so again, that's your salt bridge. Okay. On the left is where you're going to have the anode compartment, or the anode half cell. And that's just done by convention. It tends to be done such that the anode is on the left and the cathode half cell is on the right. Okay. Now, what you'll have is a piece of metal of some kind, or some sort of conductive piece of metal on either side that is your electrode. Right, so on the right, it'll be the cathode. On the left, it'll be the anode. And those will be connected. And oftentimes you'll see people write in a voltmeter in here. This is basically, that's what's measuring the potential difference between those two cells. Inside the solution, first off, the anode and the cathode are going to be made of usually a type of metal. Okay. Now, in this case, we had, based on the example above, right, we had zinc solid on one side and copper solid on the other. And I'm just going to stick with those for now until we start to get a better idea of which one is going to be which based on the actual values of the reduction potentials. So we're going to have copper again. Come on. There we go. Okay. So there's the copper solid there. Okay. A thing of note here for electrodes, there's sort of two different classes of electrodes. So you've got cathodes and anodes, but electrodes themselves can be either active electrodes, okay? So active electrodes are metals in general that are involved in the chemical reaction. Okay, and that's going to be kind of the key to this. The electrode, if it's an active electrode, it's involved in the chemical reaction, whereas if it's a passive electrode, right, it just serves the purpose. So it's a conductive substance. That is only it only needs to conduct electrons. It doesn't need to be part of the chemical reaction. And so in this case, it does matter, right? So in this particular example, and it's not in all examples, but in this particular example, the anode has to be part of this chemical reaction because of the direction of the reaction. As the zinc gives up its electrons, it's going to dissolve, which means that whole that whole electrode must be made of zinc in order for the zinc to dissolve. Whereas the copper electrode doesn't actually have to be made of copper, it just has to be some substance that will allow the electrons to come to it and deliver those electrons to the copper 2+ that's dissolved in the solution. So there are versions of passive electrodes out there. There are things like a glassy, what's called a glassy carbon electrode, right? Or a graphite electrode. Those are both conductive substances. Another one you'll see occasionally is a platinum electrode. Basically, long story short, these are all inert, okay? So they aren't part of the chemical reaction. Now, could they be? Sure, they could be part of it. The copper here is part of this chemical reaction. You're making more copper on the outside of it, sure. Now, inside the actual compartments is where you have the ions. So you have zinc 2+. Now that is going to be aqueous, right? And there might be a concentration to it. Maybe it's a some sort of maybe a 1 molar solution. We'll start to deal with concentration a little bit later, right? But you need that zinc, well, you potentially need the zinc 2+. We'll see how the concentration affects the chemical reactions a little bit later on. But you also need a counter ion in there, because that zinc 2+ had to dissolve somehow. So SO4 2- is a good one. That's a nice inert counter ion. Okay, so sulfate is the counter ion. And over here we have copper 2+, aqueous, and sulfate. Right, and so for both of these, that sulfate is going to be the counter ion. Now, when it comes to the electrodes, we talked about how the zinc electrode is going to dissolve. It's going to become less massive. The copper electrode is going to get more massive as the copper 2+ plates out on it, which means the concentration of the copper 2+ in solution on this side is going to decrease as the zinc concentration is going to increase. And we will see later that that will have an effect on the overall cell potential. Now, your salt bridge has to be just made of inert ions, okay? So you might have something like, I think we had sulfate in the last one. In this case, you could have something like a nitrate. Actually, I'll put the nitrate over here. In O3-, right? That'll move in that direction as the electrons will move through the wire in that direction, right? And maybe you'll have, if you have nitrate over on that side, I'm gonna try to make that look a little better. Nitrate there, maybe you'll have something like sodium on this other side, sodium plus, okay? And those sodium ions would move in that direction toward the other side. But they're basically just inert ions in that salt bridge. You don't want them as part of the reaction. because if you were to have, say, silver, you wouldn't want chloride as your ion in the salt bridge because that's going to precipitate out and potentially cause other issues, right? But that's the kind of the idea of these. And we're going to have another way of describing this a little later, but this is a basic drawing of a galvanic cell. We're going to have what's called line notation, which will give us a shorthand for describing the electrochemical cell, and we'll see that in a little bit. Okay, but that's how you would draw one of these. Okay. So you've got your electrodes, your salt bridge, your anode half cell or anode compartment, your cathode half cell or cathode compartment. You've got the electrons moving through the potentiometer or the voltmeter to measure this, and you've got your electrodes. So the next thing we can look at are the standard reduction potentials. And so the standard reduction potentials are the electromotive of force associated with a half reaction. That's kind of a key here. And they're associated with a particular half reaction, okay? Now, something to note, when you have this table, by convention, we always write out, you'll notice these are always written as a reduction, right? And so if we go back to our electrochemical cell above, the chemical reaction that's occurring on the left, right, zinc solid, goes to form zinc 2 plus aqueous plus 2 electrons, right? That's an oxidation. Okay. Over on the right, it is a reduction because it's the cathode. And so that would be where copper 2 plus aqueous plus 2 electrons reacts to form copper solid. But we know we can flip reactions around. We can look at the zinc, right, 2 plus 2 electrons going to form zinc solid. And when we have the setup like we have here, right, the reactions that are actually occurring here are these circled ones here, okay? And the reason why the reduction of zinc doesn't occur is because copper really wants to be reduced more. And so you have two competing reactions. These two competing reactions are written as reductions. Okay? In those competing reactions, the one that wants to be reduced more is the one that wins. And so how do we get those? Well, that's where we have this table of standard reduction potentials, okay? And so you can compare which of those reactions is more likely to occur, the reduction of copper from copper 2 plus to copper solid, or the reduction of zinc from zinc 2 plus to zinc solid. And so they're always written in the order of reduction so that we can more easily compare them, okay? So that's one of the aspects of this. We want to be able to compare these easily. But we're also writing these from the standpoint of it's a chemical reaction that occurs with something else. Because if I just have a half cell, no reaction is going to occur with just a half cell. The reaction occurs such that a reduction is paired with an oxidation. We talked about that back in Chem 101, is if you have a reduction, something else is being oxidized. And so the way this is done is we take a standard, and our standard, right, our definition is the standard reduction potential of a one particular type of an electrode, okay? It's a standard electrode. Now, these chemical reactions that are listed here in this table, and you have your appendix of your text has this type of a table to it, but these chemical reactions are done using standard conditions. Okay, and so those standard conditions are things like for the temperature, right, it's at 25 degrees Celsius, right? If it's a gas that's involved in this, right, gases would be 1 atmosphere. If it's a solution, right, if it's an aqueous solution, that solution would be 1 molar, okay? And so those are the standard conditions we're talking about, and that's how we put together this table of standard reduction potentials in order to compare which of these is going to be reduced and which is going to be oxidized. And for the reaction on the previous page, right, we can go and we can find the standard reduction potential of, oops, wrong one, where am I looking at? Copper, there it is. Starting to circle the wrong one. So the copper standard reduction potential is here. Okay. And you can see zinc has a standard reduction potential here. Okay. So what you'll notice is the copper has a more positive value, right? The more positive, the larger that positive value is, the more likely it is to be reduced. And now you can look at these half reactions as how they combine, right? And what we'll find is the difference between these standard reduction potentials is going to be the overall electrochemical potential difference that we're going to look at as driving the electrochemical cell. Okay. So before we get to that, I want to talk a little bit about why there's standard reduction potentials. And so part of these standard reduction potentials is we're comparing each of these to a standard electrode. That's why the hydrogen electrode that we looked at there had a 0 value to it. So we're going to define the standard hydrogen electrode, okay, which is governed by this chemical equation where 2 H plus, really hydronium, right? But we can look at it as H plus. Right? 2H plus plus 2 electrons will form hydrogen gas. And we're going to define that as our 0 point. And we're going to compare all other half reactions to that. Now, there are other half cells that could be used. There's other common ones that have been used over time are something called the saturated calomel electrode, which is a mercury and chloride based electrode, which has a different potential compared to the hydrogen electrode, and different procedures would call for different things. The hydrogen has been our standard for a long time, but the way that particular electrochemical cell works for hydrogen is that you have to be consistently bubbling H2 gas in. So over at the left, you can see what is a standard hydrogen electrode. So you'd have to have that half cell basically connected to hydrogen gas at a pressure of 1 atmosphere and bubble that hydrogen gas into this electrochemical cell. Now, this electrochemical half cell would be composed of hydrogen gas flowing in. You would have, so the hydrogen gas flows in, there'd be a piece of platinum wire that would be in the solution, right? And that wire would be attached to an electrode, and that electrode would be where the electrons would do their chemistry. The solution itself would be a 1 molar H plus solution. So you'd have 1 atmosphere of hydrogen going in, a 1 molar H plus solution there. So in this case, the platinum electrode, right, that's an example of a passive electrode. And you'd need a passive electrode here because hydrogen is a gas or it's dissolved as H plus. You don't have the opportunity to have hydrogen solid, so you would need another thing to conduct the electrons. And that's where that passive electrode is very important. And so the chemistry that takes place there is you can either have a hydrogen molecule come in contact with the electrode and leave some electrodes or electrons behind, causing you to make some more H plus, or you could have the reverse process there. And that's going to be governed by the potential of the thing that's in the half cell that it's connected to. But it's not always practical to have hydrogen gas as part of your chemical reaction, or having a 1 molar hydrogen ion solution. That's very acidic. So it's not always practical to have that. And so that's why you might have another type of an electrode here. And so when you were to have, if you were to have an old version is the saturated calomel electrode, that particular standard electrode has some mercury in it. Also not practical, but historically speaking, it's one of the more common ones that's been used. And it does still get used today, just less frequently. More commonly today, we actually see a silver-silver chloride electrode. So the silver-silver chloride electrode is an interesting electrochemical half cell where the silver chloride reacts with an electron to make silver metal. And so you have essentially a chemical reaction between the solid silver and some silver chloride, producing silver, chloride, and electrons. Anyway, the whole reaction here isn't the important part. The important part would be that it would be compared to a different potential. And so once you were to have that potential of the full cell with respect to a silver-silver chloride electrode, you could then convert it back to a half cell potential based on the difference between the silver-silver chloride electrode and that of the hydrogen electrode. These are things that we know fairly well, but the silver-silver chloride electrode is relatively inert compared to the other electrodes. So choosing the electrode, generally when we talk about it in general chemistry, we think about it from the standpoint of a standard hydrogen electrode, but in a research environment, they would probably be using a different type of an electrode, or maybe there are other versions as well. Okay, so we're going to generally stick to using the standard hydrogen electrode and the standard reduction potentials from the standard hydrogen electrode. So that's just a heads up that you might use other types of electrodes, but we'll generally be sticking with the standard hydrogen electrode. Okay. But those are reasons why you might want others, because when we're talking about chemical reactions take place in such a way that the conditions around those chemical reactions are very important. Okay. So we can now calculate, that should say E naught, not of zinc. Oh yeah, so it should be zinc. So we're going to look at the calculation of the standard reduction potential of zinc. So this E naught here, right, that E naught is, like the naught says standard conditions, just like it said that before, right? So you would calculate, or you would not calculate, you would actually experimentally determine the standard reduction potential of a zinc half cell by comparing it to or hooking it up to the half cell that is the standard hydrogen half cell. Okay, and so in that half cell, if you hook that up, you would wind up getting a value for this particular reaction that would give you, in your voltmeter, your potentiometer would give you a value of 0.76 volts. Okay, and so that's how all of those values up in this table are done. And so notice you have positive and negative values, right? The positive values say that those are more likely to produce, or rather the positive value says it's more likely to be reduced, right? And so zinc in this case has a value that's more likely to be oxidized. But the thing about this hookup here is, so you can sort of switch the direction of the sign that you would have in your electrode by switching the leads on here, right? Essentially, what you would find is this voltmeter is a little dumb little instrument that tells you which direction electrons are going. And if you hook up the negative end of the electrode, right, to one side and the positive to the other, and you get a positive value, if you switch them, you'd get a negative value because of the way that the instrument is monitoring the flow of electrons. And so when it comes to zinc, if it's hooked up like this, in this direction, you'll see actually a positive value here. Whereas if we really compare it, the zinc has a negative value to it, okay? So that's something to keep in mind about this. And that's why we tend to use those standard reduction potentials to calculate the standard cell potential of an electrochemical cell. Okay. So with that in mind, if we actually look at the calculating the E naught of a cell, okay, that's going to be the standard reduction potential, so E naught at the cathode minus E naught at the anode. Right? Remember, the cathode is where reduction takes place, and at the anode is where oxidation takes place. But we're going to use these values that are the E naughts. So we're considering it written as a reduction. Okay, because we're going to use those standard reduction potentials. Now, some places, some textbooks will actually flip the chemical reaction around, but you don't really need to do that. If you go directly to the table, you could say, well, the potential for this cell, right, would be the E naught for the hydrogen minus E naught for the zinc, okay? And so on this one, you would get 0 volts minus, negative 0.76 volts. And I can show you that. We'll go back up to our table, right? Here's our 0 volts right here for hydrogen, and here's our negative 0.76 volts for the zinc. Okay. And so you could figure out the whole electrochemical cell by doing that, right? And so you would wind up with a value of 0.76 volts. Okay. That's where that value up there comes from. And so our overall reaction here, right, is going to be this zinc solid reacting with H plus. So in this case, we're talking about an acidic solution to form zinc 2 plus and hydrogen gas. Now, under these conditions, if we were to think about the concentration of the zinc in solution here, it's under standard conditions. So this would be 1 molar zinc, right? And over here, we would have 1 molar H plus, okay? All right. So there's another way we can describe these solutions, and that's shorthand, and this down here, right, is what we call line notation. Okay, now I have it written out here like that so that, because I was worried about my writing when I actually put the slide together, but we're gonna have a couple things to note here, okay? What you have is, if you have inline notation, okay, the line notation shows or uses a single line to note the difference between two phases. Okay. Right, or what's called a phase boundary. And so in this case, you can kind of see that, right? Zinc solid, and then you see aqueous zinc. So there's a line that separates the two right here in the middle, right? That's our representing our phase boundary, okay? A double line is going to represent our salt bridge. Okay. And then the way this goes is you'll have on the farthest left, okay, the farthest left will be the anode, okay? And then you'll have, so on the left side, I should say, I can even get rid of the farthest left. The left side has the anode, right, or the anode compartment, okay? So the anode is going to be the thing that's the farthest left, and then the other components, right, of the anode compartment. Right, and so what you'll notice is, so we have a zinc solid is the anode. Then you have a phase boundary. And then you have the contents of the anode compartment. Now, sometimes you'll have the concentration listed and sometimes you won't. Okay, in this case, you want in particular the phase and whatever is in that phase to be there. Now, you can have more than one thing in a compartment, which we'll see when we go to the hydrogen half cell. Okay, but you have whatever information you have, you can put that in there. Here you can see after we list the contents of the anode compartment, we now have the cathode, or excuse me, we have the salt bridge. Okay, and then we have the contents of the cathode compartment. Try this again, there we go. Notice that's a big thing here. Ooh, I guess it's the whole thing, so see if I can draw this out better. Okay, so there's our cathode compartment. Okay, on the farthest right, that's going to be your cathode. Okay, you've got a couple of phase boundaries. And you'll notice that we have hydrogen in the aqueous form that's separated from hydrogen in the gas form. They're in different phases. One is dissolved and the other one is a gas that's bubbled in the solution. And so for each of them, you do want to note, well, what's the concentration for the solution? What's the pressure for the gas? And so that's going to be how you can describe all of this stuff that you have over here, right? In a very quick shorthand that we call, again, this is called line notation, okay? All right. So if we want to look at an electrochemical cell, we should, just based on different pieces of information, we should sort of be interchangeable on this and which direction we can go. If we're given line notation, we should be able to draw the cell. If we're given a cell, we should be able to draw a line notation and calculate the potential of the cell. So here we have an example that says, so the following two half cells are combined and a chemical reaction occurs. Okay, so here we want to draw and label the galvanic cell. And so that cell, we're going to describe the reaction that occurs. Remember, they're separated, so they're in separate compartments, and we need to make sure we have the good components in each of those compartments. And then we're going to calculate the potential of this cell. And then the last thing we'll do is draw out or write out the line notation for this chemical cell. Okay. So again, drawing out these cells is important so we can see what is going on in the chemical reaction. So again, we write out our anode and cathode half cells. Okay. And so it's good to just sort of start this out by drawing out your half cells, connecting them with the salt bridge, and then you can even go back and figure out which one is going to go, which side is going to have which of the two half reactions. So we're going to label these two. So this is going to be our anode compartment. And here's our cathode compartment. Okay. We've got now, not just that, we've got our salt bridge, so we can label that. Well, if we have our salt bridge, we want to put our anions over on the left side. So let's go ahead and say we have nitrate in here. Okay, because we know the anions are going to flow toward the anode, and the cations are going to flow toward the cathode. So we can maybe put here sodium ions, right? That'll go in that direction. So these are things that are somewhat generic parts of this. But now what we can do is we can go back up here and we can look at these reduction potentials and decide, right, which one of these is going to be reduced and which one is going to be oxidized. And so if we have a higher reduction potential, that's going to be reduced, and the aluminum in this case will be oxidized. Okay, which means that the chlorine half reaction will be on the in the cathode compartment, and the aluminum will be in the anode compartment. So we can look at these also now and say some other things. If we look at the phases here, chlorine is a gas, or chlorine is aqueous, which must mean we need to have a passive electrode. Over here, though, the aluminum solid can be our active electrode. So let's take over to our anode compartment. Now let's put our active electrode in there and complete our anode compartment, because that's an easy one. So we've got aluminum solid, and we would have aluminum 3+, okay, and maybe some sort of an anion that's nice and neutral. So nitrate's a good one. It's a pretty stable anion that'll give us the charge balance that we need. Okay. Then I'm going to connect my wire to my voltmeter here, and I'm going to draw in my electrons as moving from left to right. Okay. So we have now our aluminum half cell is completed, and then we get to go over and put together our electrode for chlorine. Now, since chlorine is aqueous, and in the aqueous phase and the gas phase, we need an electrode that looks a lot like this hydrogen one here, except it'll be chlorine gas and Cl- dissolved in that solution. And so what we can do is sort of draw in as good as we can, right? I'm not expecting you to be a really great artist here, because Lord knows I'm not. But here's sort of the idea of this type of an electrode. Right? You've got a little port that you can have chlorine gas coming in, right? And that would be, you generally say at 1 atmosphere if you're, we haven't actually specified that in the question, but that's where you'd have it. This could be your platinum electrode here. Okay. And then in the solution, you'd have Cl-. And you need an anion here. So let's say we have some sodium ion as well. Okay, and then we'll connect in our electrode. Okay, so that right there now gives us a nice complete electrochemical cell drawing. And we can even put in here, right, that electrons flow in that direction. Okay. So that's our drawing and labeling of the cell, except for one other thing. Right? We want to make sure we label that this is the anode and that this is the cathode. Okay. All right. Now the other thing for this, so we've drawn, right? We did our drawing, we did our labeling to describe the reaction. We can now calculate the cell potential for this reaction, right? Our cell potential, do that on the right, E0 of the cell will equal, remember it's the cell potential at the cathode, so the cathode minus the cell potential at the anode. So there would be 1.36 volts minus negative 1.66 volts. So you wind up with the cell potential here of 3.02 volts, positive value. Now for all galvanic cells, if it's a galvanic cell or a voltaic cell, you're going to have a positive value. Okay, we'll talk about what are called electrolytic cells a little later, in which you're actually putting energy in and forcing the reaction to go in the reverse direction. Okay, so there's our cell. Now the other thing we can do here is we can do our line notation. So we start out with our anode, which is aluminum solid. We have a phase boundary because we have aluminum 3 plus, try that again. Aluminum 3 plus, it's aqueous. Now I never listed a concentration here, so I don't need that. You do not need to write in any counter ions in here as long as they're inert. So I don't need to put the NO3 minus in there. So there's the aluminum 3 plus, then we've got our salt bridge, then we have our Cl minus, aqueous. Now you don't have to write it out in, as it is up here, right? So even though you have a stoichiometric coefficient of 2, you don't need that in your line notation. And then you have your the gas that's being chloride ion is being reduced. Did I do that right? Yeah. No, sorry. The chlorine gas is being reduced at the electrode. So here you can do Cl2 gas, and then you have your electrode itself, which is made of platinum. So platinum solid, okay? And so then you've got this now in line notation, okay? And so that now covers a lot of these galvanic cells, okay? And so what I'm gonna do there is I think I'm gonna end there in section 18.3. We've talked about galvanic cells. Now these reactions, remember, they are all spontaneous, and that spontaneous reaction is going to cause electrons to move from one spot to another, okay? And so when those electrons move from one spot to another, you can utilize that by having them go into a motor or charge a battery or something like that, and then you can utilize that, that energy later on, okay? What we're going to find is this is going to allow you to do a certain amount of work, and we're going to start to explore that a little bit more as we proceed through chapter 18 and our electrochemistry. Okay, any questions before we move on? Before we call it for the day and I can answer questions? Well, I guess I'll just answer my question right there. So I'll stop recording if I can. There we go.